Here we go. So what I'm presenting here is a short gamma burst population study I'm doing in collaboration with Tom Salafia from University of Milano Bicocca, in which we focus mainly on the time delay between short gamma burst events and the cosmic star formation rate. So, in order to characterize the short GFB Rashid distribution, we model it as a convolution between a fixed cosmic star formation rate whose parameters are fixed in the work from Madao and Fragos from 2017, and then we convoluted it with a probability distribution for time delays. We choose two models mainly for describing this probability distribution. One is a power law with a minimum time delay cutoff, and another one is a log-normal distribution. Once we have then the short GFB Rashid distribution, we can compute the probability of having a GFB at a certain redshift. We want also to model the luminosity distribution of our GFBs. We choose also here two models. The one is an empirical broken power law, which is a commonly used model in short GFB population studies, and the other one is takes into account a quasi-universal jet structure. So we take into account the jet emission of short gamma ray bursts, considering a dependence between the emitted luminosity and the viewing angle at which we observe the short GFB. Now, in order to constrain those parameters, we use a hierarchical Bayesian framework that's been formulated in a paper by Mendel and collaborators from 2019, in which the likelihood as this form, but without really entering really much into details, we just have to know that the nominator of this in this productory is a likelihood on the single events of our sample that takes into account the error on the measured parameters. Here at the denominator, we have modeling of the selection effects in order to also take into account for correction for Malmquist-like biases. And this term here on the right, you can recognize it as a Poissonian probability distribution that allows us to consider the local rate density of short GFBs as one of the parameters of our model. Concerning the samples that we use, they're built in the same way as in a paper from Salafia and collaborators from 2023. The first sample consists of short GFBs detected in the first 10 years of observation by Fermi GBM, for which we have a measured peak photon flux and spectral peak energy. We consider only events with above this threshold, this photon flux threshold, and the same threshold as used as a detector photon flux threshold. Maybe I say threshold too many times, but anyway, so photon flux threshold for our modeling of the detection effects of our detector. I have to stress out that in this sample we did not include GFB 17 and 17A because its measured flux is below this flux threshold, but all this process allows us to build a sample that is completely in flux. The other sample that we take into account is a sample with of short GFBs with measured redshift. In order to build this sample, we consider the short GFBs detected by SwiftBat, to which there have been applied some cuts on the photon flux, on the XRT, XRT time, and on the interstellar dust extinction in the direction of the scale position of the short GFB. We take into account also and so if we take into account also the GFBs that have been detected jointly with Fermi GBM, we have a highly complete sample in redshift, with more or less 89% of the GFB having a measured redshift associated. What concerns the results here on the left, I show you rate density curves normalized to the local rate density as a function of redshift. So that for redshift, as redshift 0, they are normalized to 1. And we see here in red and blue, we have the curves associated to the two different luminosity function models that we take into account, respectively the program power law and the structure jet model. And we see that for what concerns the power law delay time distribution, they follow pretty closely, as we said, low redshift, the cosmic star formation rate. If we want to quantify the time delay, we can do it with the statistical average of the time delay considering the delay time distribution, and we see that generally most of the time delays from the posterior samples have an associated expected time delay below 1 giga-year. For what concerns instead the other delay time distribution model that we took into account, so the log normal one, we have slightly bigger time delays between the cosmic star formation rate and the GP's bands. In particular, if you look at the broken power law luminosity model, we have two distinct peaks, one between 0 and 1 giga-years and one above 2 giga-years. For what concerns instead the luminosity functions have been constrained. Here are the on the left and the right there are the local rate density multiplied by the luminosity function curves, respectively on the left and the right for the power law and for the log normal time distribution models. And we see that we have a kind of a good agreement between the two models above 10 to the 52 ergs per second, while below that luminosity, we have that the jet model has a less steep function. Nonetheless, we have that generally below 10 to the 49 ergs per second, we have a big uncertainty on the local rate density on the parameter of the luminosity function, since we basically didn't use any information about luminosity at those orders of magnitude. Now, given our luminosity distribution rate, we can have an estimate on the joint detection rates we expect for next operating grounds. So, first of all, for the current LIGO-Ribo-Kaga observing one, we have an expected joint gamma ray percent and gradation wave joint detection rate, which is below, generally below 0.3 events per year. So if so far we didn't see any detection during 04, it's probably normal. But if we look in the future for 05, we see that this rate is nearly doubled, and we consider an observation time period for the 05 LDK run, we can expect between 1 and 3 joint detections. Now, the last thing I want to talk about is that I want to spend a couple of words about how an incorrect modeling of the selection effects can affect the estimates on the time delays. Here, what I'm showing you here are different time delay different estimates of the time delays, where we change the photon flux threshold for our detectors, and where we fix the spectral photon energy, or we apply both of those effects. And we see that if we so in blue there's the results that I showed you in the previous slides, and we see that if we apply either of those incorrect modelings of the selection effects, or if we apply both of them, we generally have longer time delays. These results here in the slides are for the power law delay time distribution model, and those biases are even more evident when we consider the log normal time distribution model. In particular, if we look at if we use an incorrect photon flux threshold for detectors, if we fix the spectral peak photon energy, we get that our time delays are closer and closer to those ones that have been estimated in the work from Van der Mar and Piran from 2015, which consider actually spectral peak energy, and they use a lower photon flux threshold. I leave you here with the conclusions. There's a paper in preparation, which I hope will be out soon, and I'm here for any doubts or questions.